sometimes reverse steps. So, what was analysis? What was the situation in year 2000? Decrease of budget and technical staff, system had to be renewed or refurbished. We had heterogeneous system structures. We need improvement of the life cycle management, and of course we had to integrate AIS and other user requirements, and we knew that there would come more and more and more. So we pretty soon realized that we had some design rules following the user requirements. We want to concentrate on maintenance personnel to react on the reduction of the personnel. We want to concentrate the technical equipment in some nodes, modular system, and so forth. So we end up with quite a lot of ropes we have to link together. That meant an holistic approach. So how to get there without getting lost with all these aspects and requirements? We selected the object-oriented paradigm with its inherent idea that you can focus on every aspect separately, subdivide the system into handleable modules, subdivide work into feasible tasks, and you also have a unified modeling language describing all the things you're doing and designing. The lesson learned is, okay, you need education on these modeling language, but you can't get education on an object-oriented paradigm because it's a way of thinking, and you never know, did you really change your way of thinking? So we did our design and we come up with a system of services, and some of you will probably have seen this picture before. The lesson we learned is, if you want to change a system, you have quite some constraints of the conservative tell you never change a running system. So that meant you have to invest quite a lot, and we did so. We invested quite a lot in explanation of the system idea. So you see the analogy between these systems, the German maritime traffic technology system layout and the shore-based ENAV architecture. And that's why it says putting a shore-based ENAV system architecture to work. What we did in this specification phase, we said, okay, we can go with the object-oriented method step by step, going further into detail, and finally we defined a generic service, and we have several of these services in our system. The lesson we learned, before you go into detail, you have to clarify your system and service principles to get the people with you. The other thing we learned is talking services as black boxes with open interfaces, yet there are no open standard interfaces for shore-based systems. Specification of the user interaction service. We compiled all the knowledge about the human-machine interfaces of our existing systems and also the system functions, and figured out, okay, we can unify this. Actually, the users told us they wanted to have unified human-machine interfaces and also unified system functions, much easier for training, for simulation. Okay, you still have some specific user application at your VTS center. You do that with today's systems by configuration. Lesson learned. Unification with a foreign coastal-wide human-machine interface requires one mandate. Otherwise, you end in an endless discussion with all the users wanting a green screen or a blue screen or a little dot on the right or on the left. Okay, up to now we only had paperwork with the specification, and we had our system running. Now we want to do the realization. We had some major aims, and I put it here to the left. That is, one coastal-wide system, concentrate the technical equipment, reorganize the maintenance personnel. And we had some conditions. Our old system became obsolete. We had to do an ongoing 24-hour, 7 days a week operation, and we had to renew quite a bit of our infrastructure as well. We call this movement from the existing system to the new migration. Lesson learned, okay, with this project, having a coastal-wide system, you need extensive project planning and management. To give you an idea what our task was, I have some numbers here, and you see we have 9 VTS centers and a couple of lighthouses and buoys, and also radio direction finders and RF links and data networks and radars. So all these had to be integrated into this one system. To give you a geographical aspect on it, you can see here our vessel traffic centers. That's the current situation. All the sensors and communication on the remote sites are connected to each center. Each center has its own radar data processing databases, VHF, and so forth. And at that time, already temporary solutions for AIS, control systems. So, bring it all together in one system. We want 3 nodes, 3 data processing centers to put all our electronic equipment which can be concentrated. We need to build up a net between these 3 centers to have some redundancy. Right now, then we have to move all our equipment into these centers, and of course we have to connect the sensors and communication means to the centers again, and of course we want to leave our human-machine interface at our operational centers, and so we also have to connect them to the centers. So the first step we had to do is we had to build up these data processing centers, which is really constructing and building work, these nodes, to build these node sites, and we did so. We had to renew some of the remote sites, and we started that process whenever we have a new service on that spot to be installed. And also we figured out that we were triggered by the technical update that we had to renew some user sites or even build new user sites, means VTS centers. And we had to renew also our supportive systems. Okay, this trigger to renew equipment is also a chance for harmonization. And again, it's another effort for the project management. So, right now, the AIS service, the realization ran very smooth because this was structured following the generic system structure, and also the implementation was done like that. The user interaction service we made in 2 steps, or make it in 2 steps. One is the human-machine interface we built as a prototype, and with the advantage that we can do the verification